Every time you hit send, a response appears with the rhythm and cadence of a conversation. But behind the interface, there is no internal library to consult, no intuition to lean on, and no consciousness to provide meaning. What we perceive as thought is actually a sprawling, invisible architecture of pure mathematical probability. Most modern systems are built on an artificial neural network. This is a framework inspired by the human brain, but instead of biological cells, it uses billions of digital nodes arranged in discrete layers. To understand how this works, we have to look past the surface and trace the exact mathematical journey a single prompt takes inside the machine. There is a fraction of a second between you hitting send and the machine generating its first word. That tiny window of execution is called inference. This animation illustrates the first step of that journey. The AI doesn't read the words you typed. Instead, it shatters your prompt into tokens, small, discrete chunks of text converted into numerical IDs so the system can process them. These numerical tokens enter the input layer and are pushed deep into the hidden layers. This is where the heavy computational lifting happens. As the data moves through these layers, it hits weights and biases. These are numerical thresholds that determine how important one piece of data is to another, steering your prompt through the network toward a specific target. Finally, the data reaches the output layer. It doesn't produce a conscious thought. It delivers a calculated probability distribution, scoring the statistical likelihood of exactly what token should logically come next. Learning for an AI involves no eureka moment. It is simply the continuous, automated adjustment of numbers until the mathematical formulas consistently produce accurate outputs. For text-based AI, like large language models, that mathematical output serves one primary job: sequence modeling. Look at this diagram showing how modern models process a sentence. This represents the attention mechanism, a mathematical process that weighs the importance of every single word in relation to every other word, regardless of how far apart they are, mapping the full context of your prompt. Once that context is mapped out, the AI acts as a highly advanced autocomplete. It calculates the statistical likelihood of the very next token, selects it, and repeats the entire process for the following word. A text AI processes information linearly. It creates entirely by addition, building language piece by piece based on probability, without ever actually reading the words it writes. Visual AI operates in a completely different reality. Image generators primarily use diffusion models, and they are trained to play an entirely separate mathematical game. Watch this process unfold. During training, the AI learns through a phase called forward diffusion. It is shown millions of clear images, and the system deliberately destroys them step by step, adding random visual static until the picture is completely obliterated. Here, we see the exact opposite: reverse diffusion. When you ask for an image, the AI doesn't pull parts from a database. It starts with a canvas of pure static and systematically subtracts the noise that does not mathematically align with your text prompt. Text models build by adding probability. Visual models create by subtracting chaos. On their own, these systems operate in totally isolated realities, blind to how the other functions. A purely text-based AI cannot see a picture of an apple, and a basic image generator cannot understand what the word apple implies in a sentence. To bridge this gap, developers engineer native multimodality, systems built from the ground up to process multiple data types simultaneously. An AI cannot directly compare a paragraph to a photograph. It uses specialized neural networks called encoders to translate everything, a word, a pixel pattern, or a sound wave, into high-dimensional vectors, which are long arrays of numbers representing semantic meaning. This visualization represents the joint embedding space. The AI uses a massive, multi-dimensional mathematical map to compare numbers. Through contrastive learning, it mathematically forces the text vector, image vector, and audio vector to sit right next to each other. To a multimodal AI, a picture of a dog, the sound of a bark, and the word puppy share the exact same coordinates in a mathematical universe. Generating static images is complex, but adding the dimension of time introduces a massive mathematical burden. This displays temporal attention. To prevent objects from flickering between frames, the AI builds a primitive physics engine, looking back to logically predict physical movement. Advanced video models simulate the mathematical physics of movement. calculating the permanence of objects even as the perspective changes to maintain the illusion of time. All of these systems share a critical flaw: they are inherently stateless. An artificial neural network suffers from severe amnesia, forgetting everything that just happened the moment a generation is complete. To hold a conversation, the system relies on a context window, a temporary scratchpad. Every single time you send a new prompt, the system must bundle up your entire chat history and refeed it back into the input layer. This creates a computational bottleneck called quadratic scaling. Because the attention mechanism compares every single word, doubling the context window quadruples the computing power required. Plus, it mathematically overweights information at the beginning and the end, while data in the middle becomes diluted. An AI's memory is not a hard drive where files are saved. It is a highly constrained mathematical arena, constantly fighting against the physical limits of computing space. Beneath the clean interface, there are only oceans of parameters, sequence additions, and noise subtractions. The machine does not understand us. But by breaking our world down into billions of statistical probabilities, it has learned to perfectly mirror our reality. The machine possesses no spark of humanity, but through billions of calculated adjustments, it has learned to map our world with enough precision to mirror it back to us.